What is our context in the cosmos? This is a kind of question that most mature minds ask when considering who we are, where we have been, and where we are going. In this brief time that we have in the universe as a living being, less than a century usually, it helps to understand more deeply our context in the cosmos if we review observations of the cosmos. This helps us understand why the universe has the properties that it does. Of course, Earth is a rocky planet. Earth has one satellite, its companion, the moon. And the Earth is in a neighborhood of other rocky planets, planets with metallic cores and silicate mantles, rocky mantles that express themselves at the surface geology of these planets. These are Mercury, Venus, Earth, and Mars. Then there's the asteroid belt, which is a very low mass, 5 times 10 to the minus 2% of Earth's mass, between Earth and Jupiter. And Jupiter, which has more mass than all of the other planets in the solar system combined. Jupiter, Saturn, Uranus, and Neptune are the gas giants. So there's this dichotomy in the solar system between the inner rocky planets and the gaseous, icy outer planets. Of course, the planets orbit the sun, and the sun is greater than 98.5% of the mass of the solar system. So the sun's composition is by definition the average composition of the solar system. Our solar system is unusual, at least for the fact that it has Earth, which has Earth life on it, but also because there is this dichotomy of two planet types. Other solar systems, so-called exoplanetary systems, seem to have a continuum of planet sizes from gas giants all the way to small rocky things and in between. Ours is different. And we're only beginning to understand why ours is different. So the night sky here, you look up there, you see, of course, if it's dark and in a place away from cities and city lights, the plane of the Milky Way and the intervening dark patches caused by dust clouds that attenuate light from the center of the galaxy before it reaches our eyeballs. We are stardust. Everything you know was made in stars. With the exception of hydrogen and helium, all the elements were formed in stars. Hydrogen and helium, on the other hand, were formed in the Big Bang cosmogenic nucleosynthesis. The ratio of hydrogen to helium in the Big Bang was about 75% to 25% almost. And all of the rest of the elements, iron, nickel, cobalt, zinc, manganese, you name it, were formed in stars. Our planet, of course, is part of a group of solar systems, about 200 billion strong, that exist in our galaxy. Our galaxy is just one of hundreds of billions of galaxies. So you have to think about scale when you consider the context of ourselves in the cosmos. We often hear that we're small and insignificant. Well, maybe that's true, but I like to say that, yeah, we're small, but we're also important. Life has existed on our planet for 4 billion years, and life probably sustains its existence on our planet thanks to its takeover of the geochemical cycles by moderating climate and even affecting the crust geodynamically. So over billions of years, our planet has remained suitable for life. The statistics are always on your side if you want to make arguments for possibility of life elsewhere in the galaxy. With 200 billion possibilities, it's a virtual certainty that there's life elsewhere in our galaxy. And there's no question that it exists elsewhere in our universe. So the first and simplest atoms, only hydrogen and helium, some lithium, beryllium, and boron were created during the Big Bang, so about 13.7 billion years ago or so. More complex atoms were created in stars. They continue to be created in stars, usually at the end of a star's lifetime. After billions of years of the star shining, it then starts to use up its hydrogen fuel and is then forced to use helium and higher mass nuclides. And in doing so, it can undergo a nova or an explosion or shed mass or even stellar mergers to create new elements. When a star dies, it expels the products, the elementary products, into space, which then form these clouds of gas and dust, which you saw in that image of the Milky Way in the sky, which in turn go on to form new stars and planets. Many of the atoms in our bodies were created in the cores of stars. So it helps to understand something of scale by using powers of 10. Of course, you remember that 10 to the 1 first power is 10, 10 to the 0th power is 1, and 10 to the 2, 3, 6, 9, 11, and so forth are just adding zeros. So this is just a shorthand for describing enormous numbers. But in scientific notation, there's also describing very, very small numbers. And I show this here, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, and so forth. So this is useful when we talk about scales of things, like our place in the cosmos. Because a schematic map of our solar system from a distance, as shown here, this graphic from Brian Fenerty, indicates that relative to the plane of our galaxy, our solar system is actually tilted. So the spin of our solar system, if you want to choose a north direction based on the spin direction of the sun, is off kilter. Hasn't always been this way. And it's also true that other solar systems are in other different orientations. There isn't a preferred spin direction, nor is there a preferred inclination. Our solar system in this configuration goes around the center of the galaxy. And so do the stars in our solar neighborhood. Here's the sun in the center, shown in red, and some close by stars, Alpha Centauri being the closest sun-like star. I just want to point out that the closest star is actually Proxima Centauri, but it's not really a sun-like star. It's a very, very low mass M dwarf. It has planets around it. We know this. In fact, it has Earth mass planets around it, which is fascinating. And these Earth mass planets are really close into this small dim star, Proxima Centauri. But Alpha Centauri is actually a double star system. It's binary. It may or may not have Earth mass planets orbiting one of the two stars or even both stars. Alpha Centauri A is a G star, so it's kind of like our star in mass, a little bit more massive. And Alpha Centauri B is a K star. So this binary star system, which is the most common configuration of star systems in our galaxy, each has a possibility of having a solar system around it as they co-orbit. Farther afield, there's Tau Ceti, Fomalhaut, Altair, Vega, Epsilon Eridani, and so forth. These are fabulously far away. Even the closest star is 4.5 light years away. For us to get there with even just the fastest space probe we have would take over 100,000 years. So maybe there's a dream of going to Alpha Centauri, but we're going to get have to use new technology in order to reach it. So galactic year is of course different from that of a terrestrial year. The solar system completes one lap around the center of the Milky Way about every 226 million years. And in doing so, it has a kind of a swinging motion backward and forward relative to the galactic center of about 15 to 20 kilometers per second. There's also a north-south swinging motion that's about 5 to 7 kilometers per second. And there is no coplanarity with our solar system, as I mentioned, and the galactic plane. So our solar system kind of bobs around in and out of the spiral arms of our galaxy, as you can show here. The orbital speed of our solar system relative to the galactic center is quite fast, over 200 kilometers per second. But then everybody else is traveling more or less at that velocity. So you can imagine our solar system and other solar systems being like fast cars on a freeway. Everyone's going fast, but they're not necessarily crashing into each other because they're all going in the same direction. The Gaia mission, launched by the European Space Agency, has revealed to us that not all stars in our galaxy orbit the galaxy in the same direction. There are some stars that orbit in the opposite direction, some that are coming through this way, others this way. So there's a bit of crazy traffic going on in the galaxy. So our Earth, of course, is the third planet from the sun. This is not to scale. But our sun is just one of 200 billion stars in our Milky Way galaxy, which itself is part of the local group of galaxies. And our local group of galaxies is in a local supercluster of galaxies. And like I mentioned, 200 billion stars in our Milky Way, maybe even more. The universe has at least that many galaxies. This is the Hubble deep space image from long exposure. Every dot you see is a galaxy. Maps of the distribution of galaxies show an interesting pattern. Here you see one of the early attempts at a map. Each little blip here is a galaxy. And you see from the northern hemisphere and from the southern hemisphere, there's a bit blocked off here because our own galaxy gets in the way. So there's occultation from stars and dust clouds in our own galaxy. There's an interesting feature of our galaxy that it's part of this local group, which itself is part of a supergroup, which itself is part of a filament of galaxies. And if you plot the distances to a large number of galaxies, as shown here by the Sloan Digital Sky Survey, and take a two-dimensional slice of the observable sky, you notice that there's a kind of foam-like pattern. It's kind of bubbles here. So the distribution of mass in our universe is uneven. So there's an enormous amount of imperfection out there. And that may be expected. What about inflation of the universe? You've heard about this, of course, the Big Bang, and the universe continues to expand. A common misconception is that there's a center to the universe. There never was a center because the universe expands everywhere in all directions at once, at the same time. Although conceptually, you can imagine at the time of the Big Bang expansion, all of the mass and energy were confined in an area, maybe a few meters, you might think, in diameter. But there is no center. This is important. The expansion or inflation of the universe can be visualized as everything in the system expanding outward from everything else. So if you can imagine dough with things like raisins or candies in it, and the dough rises, all of these bits and pieces are moving away from one another at the same time. All of reality is confined to the universe. There isn't an edge of the universe. There isn't an edge of time. We are not at the center. Nobody is. The center doesn't exist. It's difficult to grasp these concepts. So I ask you to sit and consider what I've said, that all of reality is around us. And it isn't like the universe is expanding. It's just everything is racing away from everything else. There have been attempts to model the evolution and structure of the universe to try to understand how you get these filaments, and it's an area of intense research. One other remarkable discovery that supports the idea of an inflationary universe is the so-called cosmic microwave background radiation. And the thought is the following. If the universe began as smaller, less inflationary than it is now, it must have been marvelously hot. In the intervening almost 14 billion years, the universe expanding everywhere ought to have cooled. So if one makes a temperature map of the universe using radio waves, you see that the universe's temperature is about 2.7 kelvins. And it's patchy. There's some areas where it's hotter and some areas where it's colder, as you can see here. But that is the expected result from the cooling of the universe from an initial very hot state. Another recent observation, relatively recent, is that the universe is accelerating in its expansion, in its inflation. And reasons for that are still being debated. Here's an example of a spiral galaxy, NGC 4414. This is a nice example because it's a clear, non-polar, not edge on, but sort of a little bit tilted view of a galaxy with lots and lots of dust clouds associated with its spiral arms, and a dense center. I like this picture because it helps us imagine what our own galaxy might look like from a distance. Galaxies collide. Here's a picture at the top of galaxies in the process of colliding. It's anticipated that about 2 billion years from now, our nearest neighbor galaxy, Andromeda, will collide with us. But this collision has little or no effect. It'll cause stars to move around and perhaps be ejected. There may be merger of the two galaxies, but it's not like stars will be banging into one another. And that's because the mean free paths we're talking about here are extraordinarily long. Mean free path is the distance that you could travel before you strike something. And because stars are many light years from one another, it's like the two galaxies gravitationally interact with one another, but it isn't like it's a giant crash. Here's another galaxy. This is a polar view, the Whirlpool Galaxy M51. Very, very dust rich. So there were lots of stars in this galaxy that went through their lifetimes and at the end of their stellar lifetimes cast dust and gas into interstellar space, which is then coagulating, collecting gravitationally, and the result is stellar nurseries. So interstellar gas, of course, can increase in density by collapsing under its own gravity or by being juiced or pushed by a nearby bright star or supernova that is injecting mass and energy into the cloud, which can cause it to start gravitationally collapsing into clumps, which then can lead to new star systems. And then stellar winds and explosions after these star systems finish their lifetimes, return material to interstellar gas and dust. That is different from what it started. And this is called galactic chemical evolution. So the formation of our solar system follows this path. Solar system formed within a giant interstellar cloud of gas and dust, and the solar nebula collapsed under its own gravity. Here's an example of newborn stars in the Orion Nebula. Stars are born in stellar nurseries. So you have perhaps dozens, perhaps hundreds, perhaps thousands of stars forming in these stellar nurseries, and then they co-orbit one another before they dissipate into the spiral arms of the galaxy. Eagle Nebula, M16 here, is one of the most famous examples of these so-called pillars of creation. A closer look at this show budding type structures where stars have captured gas and dust around them gravitationally, and nearby very bright young stars are blowing gas and dust away from the interstellar medium. But because some of the gas and dust is held to these young stars, there is like a bud there. And so because the star holds on, it's not going to lose the gas and dust because of these nearby stellar winds. So the formation of our solar system was from gravitational potential energy that converted to heat. You have light years across some of these clouds of gas and dust that collapse. That's an enormous amount of potential energy. And the sun formed in a dense hot center from this collapse. And a shrinking nebula rotated faster until collisions caused the nebula to flatten into a disk. This is an old idea. Immanuel Kant in the 18th century thought of this by observing clouds and whirlpools as a means to explain why all of the planets in our solar system go in the same direction around the sun and follow the plane of the ecliptic. So they have a They're coplanar one another. And this is the best way to explain that. Since that time, it's a remarkable insight. We've seen this actually occurring. So protoplanetary disks are this product when a young star collects and captures and gravitationally binds gas and dust from the interstellar medium. These proplids are observed, as I mentioned, around young stars. And if you block out the central star, as shown in this figure, you can see new planetary systems in formation. This is happening as we speak. So the idea then is, over time, these disks of gas and dust around the star clear out thanks to planet formation. And once the star brightens and goes into its main sequence, it blows out the rest of the gas a few million or maybe tens of millions of years into its early history. So the Pleiades, a popular group of stars, show stars born in neighboring nebulae, and they're moving apart from one another in this dissipation behavior that I mentioned, and clearing their gas. Planetesimals are the first large objects to form in this environment around young stars in the planet building process. The idea, of course, is that you go from dust to clumps, little pebbles and rocks that then grow under their own gravity into larger things called planetesimals. Something about the size of the moon or the large asteroid Vesta. These evolve gravitationally. What happens is that when gas is still present in the nebula, the planetesimals interact with the gas and one another, and they start crashing into one another and grow into what are known as planetary embryos, something about the size of Mars. It's important to consider condensation if we go back to trying to understand this dichotomy in our solar system that I mentioned, where the inner solar system has these rocky metal worlds and the outer solar system has these icy gaseous worlds. Condensation of material from the solar nebula depends on temperature, just like condensation of anything. Planet composition depends on distance from the sun. The closer you are to the star, the more refractory, high temperature condensates you'll get out, like metals, like rock. So think of these things like ceramics, as opposed to farther away from the star, where condensation can occur at much lower temperatures. Think ice and gas. Ice is condensed only beyond the so-called frost line. The frost line is a distance from the star at which water condenses out as ice. The Jovian planets, these gas and ice giants, formed by pulling gases into large cores early in the cold outer solar system, where there was lots of gas. So within the frost line, rocks and metals condense. Beyond the frost line, hydrogen compounds and rocks and metals condense. There are four main ingredients of the planets. They're metals, rocks, ices, and light gases. Metals are things like iron and nickel and aluminium. These have very high condensation temperatures, over 1,000 kelvins. But the abundance by mass is very small, 2 times 10 to the minus 1% of all of the elemental material in our solar system. Contrast that with light gases on the right side of this diagram. Hydrogen and helium are in that category. They do not condense in the nebula. They come out, they become reactive, and they make water, and helium, of course, is a noble gas. 98% of the mass is hydrogen and helium. But let's look at rocks. They're lower temperature condensates with respect to metals, 500 to 1300 kelvins, 4 times 10 to the minus 1%. And then ices, so hydrogen compounds, water, methane, ammonia, very low temperature, below 150 kelvins. But a bit more, almost 1.5% of the elemental inventory of our solar system. And I think you can see the dichotomy here. To the left, look a lot like rocky planets, and then to the right, look a lot like the Jovian planets, the gas giants. Whence these elements? Where did they come from? Well, nuclear fusion is the origin of the elements, mostly. The elements that we concern ourselves with mostly, but not exclusively. So this explains, for instance, the relative abundances of the elements. You see in this lower left diagram here, the relative abundance on the y-axis against the atomic number, so higher mass element on the x-axis, has hydrogen and helium way at the top. But then it declines when you get to higher and higher mass, except for this funny thing here at iron. You see, this is called the iron peak. And that's because iron is, and nickel, these are the two most stable configurations of protons and neutrons in an element's nucleus. So here is another view of the composition of the solar system, the abundances of elements of the solar system. Hydrogen and helium on the left, and then lithium and beryllium are unusually low because they're consumed in stellar nuclear reactions. But then carbon, oxygen, magnesium, silicon, sodium, etc., they're pretty high. And then it kind of declines, and then there's this peak at iron, and then it appears to show a monotonic decline. All the way on the right are the ultra heavy elements, thorium and uranium. These are not stable elements. They've got very long half-lives, 14 billion in the case of thorium-232, and uranium-238, 4.4 billion years half-lives. Very slow decays. Notice that the elements significant for planet building, like our rocky inner solar system planets, are abundant. Oxygen, silicon, magnesium, iron, nickel, etc. This sort of pattern of composition is not unique to our solar system. It seems that most sun-like stars show this kind of composition, which we think ought to be expressed in the planets that orbit such stars. But how do we make sense of this distribution of the elements? Well, we have to talk about stability. So stars are unstable at the end of their lives. Some stars, like this one, supernova 1987A, blow up. These are stars that are a lot more massive than our star. Our star will not do this. Our star will simply expand and go into what's known as an asymptotic giant branch phase, as a red giant, and then it'll shed gas and dust and squish down to a white dwarf, which is not even a star. So to explain this, we have to think about stability of elements and building elements in nucleosynthesis in stars. To do that, why don't we flip it over? And you see how when I do that, the diagram goes from hydrogen and helium down here at the bottom all the way up and then flattens out. This looks a lot like the binding energy curve of the element. So what this is if you calculate the difference in mass between adding up all the protons and neutrons in the nucleus of a particular atom, of a particular element, you get a number that is different from measuring the nucleus of that element itself. So this is called the so-called mass defect or the binding energy. And the reason for that is that as the protons and neutrons come together and they bind to one another in the strong nuclear force, there's a duality of energy and mass. So the binding energy curve with increasing binding energy shows increasing stability of that element. Notice hydrogen and deuterium, so-called hydrogen 2, are at the low end of the scale in the lower left. But right at the top there is iron and copper and so on, and then it kind of levels off. The important point here is that that iron peak that I mentioned in the distribution of the elements is because of iron stability. Stars can make elements pretty easily. They get energy out of making these elements all the way up to iron in the fusion process. But after iron, nickel, a star has to add energy to build heavier nuclides, heavier elements, the ones that are on the right side of this diagram. And so that's an energy consuming reaction. And that means that there's just going to be less of that material because it's more difficult to make these elements. Many of the elements that form in this pathway to the right decay. So they decay by fission. You think about uranium and thorium as good examples of this. So ultimately, the elements are reaching a peak at iron with the greatest stability. Of course, to do that in the whole universe is going to take many hundreds of billions of years to accomplish the so-called iron, the iron enhancement of the universe. So binding energy, as I mentioned, is the difference between the mass of just adding up the protons and neutrons and the actual mass of a nucleus of a particular atom, of a particular element. So this ingredients list that I showed you and just explained went into building our solar system. The planets accreted from condensed materials. These condensed materials stuck together, then attracted one another by gravity to form planetesimals. These collided and combined to form protoplanets or planetary embryos. And only planets with this sort of well-behaved orbit, sort of coplanar, rather circular, end up surviving for the most part. There's certainly chaos involved here. But in the last stages of planet formation, we anticipate that there are massive collisions, such as the one that formed our own moon, such as the one that may be responsible for Mercury having a very large core and a thin rocky mantle, such as one considered responsible for the moons of Mars, Phobos and Deimos. Interestingly, why does Venus have no moon? So here is our duality, our dichotomy of our solar system. Terrestrial planets, smaller in mass and size, higher density, rocks, metal, solid surfaces, warm, close to the sun, few moons or rings. Jovian planets, huge in size and mass, lower density, no solid surfaces, farther from the sun, colder, with many, many moons and rings. So there's this inner and outer solar system dichotomy. This was established, we think, very early on in the history of our solar system. But again, there is apparently no example in our solar system of a continuity of planet sizes from Jovian planets to the terrestrial type planets. It's a duality. Other solar systems show a continuum in sizes. Why there is this difference is a matter of enormous debate right now. Of course, our solar system has 8 planets. Pluto has been demoted because it is not coplanar with the other planets in our system. And it has a highly eccentric orbit, so that there are times when Pluto is closer to the sun than Neptune is. That brings us back then to the scale of the solar system. If you want to know the context we have in the cosmos, know your origin, know why we have the elemental inventory that we do, know why we have these inner rocky metal planets and outer gaseous icy planets. Know that the distances and the length of time that we're talking about are vast. And yes, we are small. I don't think we're insignificant. And I do think we're important because we, as far as we know, are the singular example of the universe viewing itself. That concludes day 2 of our travels and musings of a natural scientist.